To prove cos squared theta plus sine squared theta is equal to 1, we first of all are going to sketch our unit circle. So what we know about the unit circle, we're going to give it a center O, and we're going to have a point P somewhere on the circle here in the first quadrant. And what we know from before is that any point on the unit circle can be expressed as cos theta sine theta. Theta being the angle created here with the x-axis. And what we can do is we can label our right angle triangle the length of OP, which is our radius, because it's the unit circle, is 1. The height of that triangle is sine theta, our y value, and the base of that triangle is cos theta, our x value in our point. And what we're going to look at is using, first of all, the distance formula. And we're going to use the distance formula to find the length of OP, the distance from the center to the point. My x1, y1 being cos theta sine theta, and my x2, y2 being 0, 0, my origin. So when we fill into our distance formula, we'll get x2, which is 0, minus x1, which is cos theta, all to be squared, plus y2, 0, minus y1, which is sine theta, to be squared. Now we know that the length of OP is equal to 1, so we can put that equal to it straight away. So we have 1 is equal to the square root of minus cos theta squared is going to give me cos squared theta, plus minus sine theta squared is going to give me sine squared theta. I don't want the square root, so if I square both sides, I get 1 is equal to cos squared theta plus sine squared theta. And that proves our identity. To prove the sine rule, we're going to focus in on two of the fractions of the sine rule first. And we're going to look at two different situations. We're going to look at it from the point of view of using an acute angle triangle. And then we're also going to look at it by using an obtuse angled triangle. So first of all, drawing out our acute angle triangle. We draw a triangle something like this. We can label it with our A, B, and C. Therefore, our side A, B, and C. And we're going to draw a line perpendicular to the base, and we're going to call that H in length. We have our angle A, and we have our angle B. And in this triangle, we're going to look at the two different right angle triangles we've just created with that line H. And what we can say is that the sine of A will be equal to H over B. That's looking in the left-hand side triangle here, which means we can say that B sine A is equal to H. In the right angle triangle to the right, with the angle B, we can say that the sine of B is equal to H over A. Therefore, A times the sine of B will be equal to H. And if both of those are equal to H, therefore, B sine A will be equal to A sine B. If we look at it from the point of view of an obtuse angle triangle for a second, we're going to try and do something similar. So again, we have A, B, and C. We have an angle A and an angle B that we're interested in. And outside this triangle, I'm going to draw my perpendicular line. And again, I have a height of H. This is my side B, A, and C. What we can say about this triangle is that the sine of A is equal to, looking at the right angle triangle we've created there with H over B. Therefore, B sine A is equal to H. Similarly here, instead of looking at the angle B, we're actually going to be looking at this angle here, which would be considered to be 180 minus B, because it's on a straight line. So we're going to look at the sine of 180 degrees minus the angle B would be equal to H over A. Therefore, A times the sine of 180 minus B is equal to H. Now, since 180 minus B would be in our second quadrant in our unit circle, and it has a reference angle of B, sine is positive in the second quadrant. Therefore, we can say that H is equal to A times the sine of B here also. So therefore, like in our other situation, B sine A is equal to A sine B, as our two H's are equal to each other. So in both cases, if we divide by sine A sine B, we will end up with A over sine A equals B over sine B. So that again is in both cases if we divide by sine A sine B. Okay. Similarly then, it may be shown that A over sine A equals B over sine B equals C over sine C. And that's our identity, or the sine rule, proven. To prove the cosine rule, we're going to first of all draw a triangle. This triangle is going to have one of its vertex or corners is going to be point A here, which is on the origin. We are going to have another point here on our x-axis, which is B, and we're going to call that the point C0. And then it will have a point C over here as its other vertex, making an obtuse angle. So we join those together, we'll make our triangle circle. What we'll then do is we're going to draw a circle with a radius length of AC, okay, which would be, in theory, lowercase b is a side, okay, given that this would be the angle B, this would be the angle A. So we're going to draw a circle with that radius. Since any coordinate on any point on the unit circle can be written as cos theta sine theta, what we're going to do is apply something similar here. This is my angle A. This length here is B. What we can call the point C is B times cos of A and B sine A. We can label our side BC as lowercase a, and we already know that AB is lowercase c in length. If we use our distance formula here and look at the length of BC, so the length of BC would be, using our 2 points here, we would have x1, y1, and x2, y2. So it would be the square root of x2 minus x1 to be squared plus y2 to 0 minus y1 all to be squared. We already know from our diagram here that BC can actually be expressed as A, and it will be the square root again, C minus B cos A to be squared plus minus B sine A to be squared. If I square both sides, I end up with A squared is equal to squaring my, well, first of all, we'll get rid of the square root. We do have to square out these brackets then. Minus b sine a is squared. We could do that now if we wanted to, and express it as b squared sine squared a if we wanted to. Squaring out this bracket then, we're going to end up with c squared minus 2b c cos a plus b squared cos squared a, and then our plus b squared sine squared a. We can tidy that up a little bit. We have some common factors here. So we can say that a squared is equal to c squared minus 2bc cos a plus, if I take the b squared out here, I'm left with cos squared a plus sine squared a. And we already know our identity, that cos squared a plus sine squared a is equal to 1. So if that is the case, that a squared equals c squared minus 2bc cos a plus b squared. If I just rearrange that slightly, I can say that a squared is equal to b squared plus c squared minus 2bc cos a, therefore proving the cosine rule. Similarly, it also may be proven that b squared is equal to a squared plus c squared minus 2ac cos b, and also c squared is equal to a squared plus b squared minus 2ab cos c. To prove cos a minus b is equal to cos a cos b plus sine a sine b, I'm going to first of all draw a unit circle. It's going to have a center of O. And first of all, I'm going to draw a radius going here to this point. And that's, I'm going to label with one angle in a second, and the other radius I'm going to draw is over here. So the full angle to start with, if I start with that one, that's going to be labeled the angle A, making this the point, we'll call it P cos A sine A. The acute angle created here with the other radius that I drew, we're going to call that the angle B, and therefore we can call that Q cos B sine B. We then can also look at this angle here. And that angle there can be written as A minus B. So starting this proof, we're going to look at the length created by the side opposite that angle of A minus B, and that in this case will be the side length PQ. We're going to do that in two different ways. The first way that we're going to try and find the length of PQ is using the distance formula. So that would mean that PQ is equal to the square root of cos A minus cos B to be squared plus sine A minus sine B to be squared. Squaring both sides, we get PQ squared is equal to cos A minus cos B to be squared plus sine A minus sine B squared. And the next step is to square out those brackets. So we will get PQ squared is equal to cos squared A minus 2 cos A cos B plus cos squared B plus sine squared A minus 2 sine A sine B plus sine squared B. Now what we'll notice here is that we have cos squared A and we have sine squared A, and we have a cos squared B and a sine squared B. And what we know from our previous formulas and identities is that cos squared A plus sine squared A is equal to 1, and also cos squared B plus sine squared B is equal to 1. So therefore, we can write that as PQ squared is equal to 2 minus 2 cos A cos B minus 2 sine A sine B. The reason for that, cos squared theta plus sine squared theta is equal to 1. So bringing those two together, that's where that 2 has come from. What else we can do here? We have a common factor in these two parts, so we could also factorize there, leaving it as 2 minus 2 bracket cos A cos B plus, because I'm taking the minus out, sine A sine B. And we're going to leave it at that. There's not much more I can do with that. We're now going to do, or try and find the exact same thing, P, the length of PQ, but this time we're going to use the cosine rule. So using the cosine rule, what we will have is PQ squared will be equal to OP squared plus the length of OQ to be squared minus 2 times the length of OP times the length of OQ by the cos of A minus B. Filling in what we have for that, we know that OP is the radius of the unit circle, so that's 1 squared plus again 1 squared for OQ minus 2 times 1 times 1 comes by the cos of A minus B. So we can say that PQ squared is equal to 2, bringing those together, minus 2 times the cos of A minus B. So we now have two different ways of writing PQ squared. And if they are both equal to PQ squared, then we can put them equal to each other. So equating both of those, we can say that 2 minus 2 times the cos of A cos B plus sine A sine B is equal to 2 minus 2 times the cos of A minus B. There's 2's on both sides. We can take away 2 from both sides and they will cancel each other out. We can also divide both sides by minus 2 then, which will mean they will also cancel each other out. And what we're left with is cos of A cos B plus sine A sine B is equal to the cos of A minus B. And that proves our identity. To prove that the cos of A plus B is equal to cos A cos B minus sine A sine B, we need to use our formula cos of A minus B is equal to cos A cos B plus sine A sine B first. And what we're going to do is we're going to replace B with minus B in that formula. So that's going to look like the cos of A minus minus B is equal to cos A cos minus B plus sine A sine minus B. Some things that we need to make sure we understand from here is that we know that the cos of minus B is equal to the cos of B. That can be found on page 13 in your log tables book. And also that the sine of minus B will be equal to minus the sine positive B. Again, on page 13 in your log tables book. So using that information, we can therefore say that the cos of A plus B, or double negative here making us a plus, is equal to cos A, cos of minus B can be written as cos of positive B. And here, because we have the sine of minus B is going to give me a minus sine B, it's going to change my sign in front. So minus sine A sine B. Therefore proving my identity. To prove that the cos of 2a is equal to cos squared a minus sine squared a, we're going to use our previous identity of cos a plus b is equal to cos a cos b minus sine a sine b. And what we're going to do is we are going to replace b with a. Okay, so when we replace b with a, we get the cos of a plus a is equal to cos a minus sine a sine a, giving us the cos of 2a is equal to cos squared a minus sine squared a, proving our identity. To prove that the sine of a plus b is equal to sine a cos b plus cos a sine b, we're going to start with the identity that cos of a minus b is equal to cos a cos b plus sine a sine b. And what we're going to do is we are going to replace a in that identity with 90 degrees minus a. So that's going to give us cos of 90 degrees minus a minus b is equal to cos 90 degrees minus a cos b plus sine 90 degrees minus a sine b. Now what we need to know here is that the sine of 90 degrees minus a can be written as cos a, and that the cos of 90 degrees minus a can be written as sine a. And where does that come from? If I just very quickly just show you with a quick sketch. If I have an angle A in this right angle triangle, here's my 90-degree angle. This angle here can be called 180 degrees minus 90 minus A, which ends up being 90 minus A. When I label my triangle, we know that this is my hypotenuse, this is my opposite, focusing in on the angle A obviously, and this is my adjacent. So for example, if I'm looking at the cos of A, I would call that the adjacent over the hypotenuse. But if I was looking at the sine of 90 degrees minus A, opposite 90 degrees minus A is my adjacent, and the hypotenuse is the same. And that's where it comes from. Okay, we can show that they are equal to each other. And that's not something that you have to show within this proof, but just in case we're not sure where that comes from. That's just a quick idea of that. So once we know these, we can use them within this identity. Again, not having to show them or prove them in any way. So what we can say is we have the cos. We'll deal with that in a second, but I'm going to leave that as it is for now. is equal to the cos of 90 degrees minus A, we can replace with sine A, multiplied by cos B. The sine of 90 degrees minus A, we can call cos A, multiplied by sine B. So the right-hand side is exactly what we need. Here, I'm going to rewrite that as the cos of 90 degrees minus, if I take the minus out here, A plus B. Just a slight rearrangement of what we have. That's equal to the right-hand side. In doing that, what we can say is, here we have the cos of 90 degrees minus an angle. And the cos of 90 degrees minus an angle, we can call the sine of A, in this case, the angle here being A plus B. So we can rewrite that as sine A plus B is equal to sine A cos B plus cos A sine B, therefore proving our identity. To prove that tan of A plus B is equal to tan A plus tan B all over 1 minus tan A tan B, we first of all look at our identity on page 13 telling us that the tan of an angle is equal to the sine of the angle over the cos of the angle. So that means that I can rewrite tan of A plus B as the sine of A plus B over the cos of A plus B. And I can expand out those using the identities and the compound angle formulas that I've already looked at. So sine of A plus B is sine A cos B plus cos A sine B all over the cos of A plus B, which is cos A cos B minus sine A sine B. What we have to do now is divide numerator and denominator by cos A cos B. As long as we divide top and bottom by the same thing, we're just changing how it looks, but not its value. And cos A cos B, that should say. So cos A cos B will allow some elements to cancel. If we look here, cos A cos B in our denominator, if I divide by cos A cos B, I'm going to get that 1 that I have there. So let's have a look and see what that looks like. So what we can say is that the tan of A plus B will be equal to sine A cos B over cos A cos B plus cos A sine B over cos A cos B. So that's our numerator divided. And we do the exact same for the denominator. So cos A cos B divided by cos A cos B minus sine A sine B over cos A cos B. And we look and see, is anything going to cancel? So our cos B's here will cancel. Our cos A's will cancel here. Here, our top and bottom cancel, leaving us with 1. And for the moment, it doesn't look like anything really cancels here. However, what we're going to look at now is what we're left with. What we know is that tan is sine over cos. So if I have sine A divided by cos A, which I have here, I can rewrite that as tan A. Here I have sine B over cos B. Again, that can be rewritten as tan B. I have the 1 minus And here, if I was to split these two fractions up, we technically have sine A over cos A multiplied by sine B over cos B, which we can rewrite as tan A multiplied by tan B. So using what we have there, we can say that tan of A plus B is equal to sine A over cos A, again, gives me tan A, plus sine B over cos B, we can rewrite as tan B, over 1 minus sine A cos A gives tan A, multiplied by sine B over cos B, tan B. Therefore proving my identity.